Welcome back to Linear Algebra. Today we're going to introduce the first bit of our more abstract and proof-based math. So here are vector spaces. And we've been working with a specific vector space so far in the course. But what is a vector space? Well, a vector space is a collection of vectors and two operators. So this is the plus and multiplication, or the dot, such that the following hold for all vectors and all real numbers. So there are 10 axioms that have to be satisfied here. So 1, if we have two vectors u and v, the sum also has to be in v. This is important. The order in which we add things should not matter, and if we're adding a bunch of things, we should be able to group them however we want. So this is the associativity and commutativity that we've seen before. We need to have a zero vector. We need to have an inverse for every vector. So if we have a vector u, we need an inverse negative u that gets back to 0. So we should always be able to get back to that 0 vector. Those are the addition rules. Multiplication, if we have a vector u, then for any real number, we should be able to multiply that vector by a real number and also be in our vector space. We've got some distributive property here. So if we have a vector u plus v multiplied by c, it should be cu plus cv. If we multiply a vector by two scalars, so c plus d times u, we get cu plus du. If we multiply c times du, it should be the same as cd times u. And of course, we have our identity, so 1 times the vector u should be the vector u. So you're saying, hold on a second, we've already proven these, we already looked at these. Why are you telling me this? Well, this is more abstract. So we've been working in the real numbers. So let's talk about different things that may or may not be vector spaces. So for instance, we know the real numbers. This is a good vector space. However, here's a question. Is V the set of all vectors xy where x is greater than 0 and y is greater than 0 a vector space? So if we take a look, I really don't want to draw R2, but we're asking, is all this area right here, is this a vector space? So we have to ask ourselves, does it satisfy the axioms? And there's a ton of axioms here, so I'm going to circle the two that you should focus on when you're trying to disprove vector spaces. So here's one. Let me do that in yellow. So u plus v needs to be in there, and if we multiply by a scalar, it also needs to be in our vector space. And this scalar can be any number in the reals, positive or negative. So let's think about this. Okay, so let's say we have a vector like this. It goes out to xy, it goes to this point. So this is our vector xy. Let me erase these yellow bits. Now, is there anything we can think of? So we have u plus v has to be in v. So if we take another vector that's in this space, we can add them together. It's going to still be up in this first quadrant here. So that's fine. That's fine. But what if we take a scalar here? So what happens if we scale this by -1? So let's take -1 xy. Well, what happens then? Well, then we end up over here. And this isn't good because we've exited our vector space. Our vector spaces have to be closed under addition to multiplication, which means we should never be able to leave this area up here. But if we multiply by -1, we can leave our vector space, and that's not good. Therefore, this set here is not going to be a vector space because we don't want to be able to leave it. Okay, that's the first example. What about this second example? So here I have x times y is greater or equal to 0. So if we draw this, this is a little bit different. So we're allowing this space up here because if we have a positive times a positive, it equals a positive. But we're also allowing this area down here. So a negative times a negative is equal to positive. So this looks good, right? Okay, well, to disprove this, we want to end up with a vector somewhere in this space or somewhere in this space. And we can do this by adding or by multiplying. Now, what happens if we multiply? what if we take any vector u and multiply it by some scalar c? Well, if it's up here, we're going to end up down here. And if it's down here, we're going to end up here. So these multiplication tricks aren't going to work for this one. Instead, we should probably find two vectors when added together that aren't going to be in our vector space. So we can draw this out and we can kind of see. So visualizing these things is a pretty good tip, especially at the beginner level. Normally you shouldn't because things can get abstract really quick, but just for the sake of showing you, let's draw two vectors that ends up somewhere in this space. Okay, well we can do one that's pretty straight up, and then we can do one that goes to the left a lot. So when we add these two together, let's do this with brighter yellow, we'd end up somewhere in here. So what could that look like? We just have to find one pair of vectors that do this. Let's think about this. We want like 1 to the right and 2 up. And then we want something like 3 to the left and 1 down or something. So we could do -3 and we could do 1. Wait, this does not work. This also has to be -1. So remember, we have to have that x times y is greater or equal to 0. So when we choose our vectors here, we have to make sure that both of them are in our vector space. So we're good here because 1 times 2 is greater than 0. We're good here because -3 times -1 is greater than 0. So this is going to give us -2 and 1. And we can see here that our x times y here is definitely not greater than 0. Therefore, this is also not a vector space. So you can see we're pretty limited to what our vector spaces are. If we're working in the plane R2, it's probably going to have to be most of R2. Now, of course, there are some exceptions here. We'll talk about those eventually. But drawing diagrams like this and visualizing, especially when you're first starting, is a great way to figure out what a vector space is. So you have to play with numbers, you have to play with these axioms and see which ones are violated. Again, these two are great to check to see if they're violating. Another one to check that is usually on trick questions is the 0 vector in your vector space? Because sometimes you may be given vector spaces where you can't get the 0 vector, and those are not vector spaces, so you must check for those. Okay. Here's one that might surprise you. Polynomials are a vector space. So for instance, we can write a polynomial as a0 plus a1 times t plus a2 times t squared, and this just goes up to some t to the n. So this might be a new notation for polynomials if you've never actually looked at polynomials before, but these are just constants, these a0s and a1s, so you can kind of see they look like vectors. So we need some notation here. The degree of a polynomial is going to be the highest power of t that is non-zero. So in this first example, assuming that a is not equal to 0, then the degree of this polynomial would be n. So that's n degree. So for an example, what is the degree of p, where we have the polynomial 43t cubed plus 6 plus 2t to the 4 plus 6t to the 7 halves? Well, this is the same thing as 3.5. Our highest power is t to the 4, so the degree of the vector p, or the polynomial p, is going to be 4. The polynomial with the 0 degree is the 0 polynomial. So this is usually just, again, written as a 0. So this is the nice thing about when talking about vector spaces is we know what the 0 means. This could be the 0 for anything, so we just use the same symbol here to denote that. So the 0 with the bar under it, that's good. In fact, for polynomials, sometimes it doesn't even have the bar. Okay, so let's verify the axioms for polynomials, because I kind of just told you that it's a vector space, but you might not believe me, so let's prove it. First of all, if two vectors, or two polynomials, are in the space independently, then their sum has to be in the space as well. So I've listed p and q, and we can add these together. So for instance, pt is going to be a0 plus a1t all the way up to an t to the n. And then we're going to add our vector qt. This is going to be b0 plus b1t all the way up to bn t to the n. I should mention these are the same degree, but they don't have to be because these are polynomials. So we could add a 4-degree polynomial with a 7-degree polynomial, and their end result would be the 7th-degree polynomial. You do have to make sure that if you're working in 7-degree polynomials, you are in P7. This is Pn specifically, so this has to be less than or equal to that n. Okay, so now what we can do is we can group things up. So we can take a0 plus b0, then we can add a1 plus b1 times t. This will go all the way up to an plus bn times t to the n. So this is in our space. This is good. All of these are good. Therefore, this axiom is satisfied. What about if we have polynomial p plus q, this is equal to q plus p? Well, we already have this first part here, so I'm just going to take this and we'll write it down, and we know that we can switch the values of this, right? We know that we can write this as b0 plus a0, because these are just real numbers. We've already worked with these. This is b1 plus a1t, all the way up to bn plus an times t to the n, and then we can separate these again. So we can expand, and then we would end up with b0 plus b1t plus all the way up to bn t to the n. And then we could add our a0 plus a1t all the way up to an t to the n. So the second axiom is good too. What about this third one? If we take a constant and we multiply it for all c, well, first of all, we have a0 plus a1t all the way up to an t to the n, and let's multiply that by some constant c. Well, then we just end up with c times a0 plus c times a1 times t all the way up to can times t to the power of n, and we're good. So these were 3 of the axioms. With these 3 axioms, you can prove everything else pretty straightforwardly. So if you want the practice, you can prove the remaining 7, but you really don't have to, because you should see things follow from this pretty simply. For practice, though, I'd suggest doing it. But that is it for vector spaces. Next video is subspaces, and I'll see you guys then. If you have any questions, please leave them in the comments below, and I'll answer them as quickly as I can.